Welcome, and here in section 2 of chapter 8 we're going to be looking at parallelograms. And so we first start off with the definition of parallelogram. And a parallelogram is a quadrilateral, which tells us what about the parallelogram? That it has four sides, with both pairs of opposite sides parallel. Okay, so that's our definition. There are other possible definitions for parallelogram, but we're going to work with this one. So we want to use that idea to prove that a diagonal of a parallelogram divides it into two congruent triangles. We'll just do a real brief informal proof here. So if we have parallelogram ABCD, and we know by definition that AD is parallel to BC and AB is parallel to DC. Therefore, by alternate interior angles, we know that these two angles are congruent, and also by alternate interior angles, these two angles are congruent. Put in there with the reflexive property that DB is congruent to itself, and we have the two triangles that are congruent by the angle side angle theorem. So that is theorem 8.8. Each diagonal of a parallelogram separates the parallelogram into two congruent triangles. Now notice it's theorem 8.8, and then we're coming back to theorem 8.3 and so on. I feel that this is a better basis to getting us started with the parallelograms and explain some of the other things about the parallelogram. So what can we know because we have those two congruent triangles there? Well, if the triangles are congruent, then we see that the opposite sides have to be congruent because they're corresponding parts of the congruent triangles. What other corresponding parts of the congruent triangles do we have? Well, theorem 8.4 then gives us that the opposite angles are congruent. Again, easily shown from theorem 8.8 by looking at the corresponding parts of those triangles. Theorem 8.5 then gives us that consecutive angles are supplementary. Now that's not from the congruent triangles, but rather just from the fact that we have the parallel sides. So the consecutive angles are consecutive interior angles that we learned about back when we learned about parallel lines. And so those are supplementary. And then theorem 8.6, if a parallelogram has one right angle, then it has four right angles. So those are some things that we know just from kind of the basics of the definition and the diagonal dividing it into two congruent triangles. So that gives us some information we need to start working with the triangles. So if we have this, or with the parallelograms rather, so if we have this parallelogram, we want to find the measure of angle URT. So let's mark angle URT. Here's this angle. And we see that with the parallels here, that angle URT and the 40-degree angle over here are alternate interior angles. So that's all we need. We know the measure of angle URT is 40 degrees. For angle RST, angle RST is this angle. So we have angle UTS, which has a measure of 58 degrees. So we see consecutive interior angles there, and we know that angle RST has to be supplementary to the 58. So 180 minus 58 gives us that the measure of angle RST is 122 degrees. Okay, now looking at some other parts, the sides here, we see that the 3y and the 18 are opposite sides. And we saw by one of our theorems that in a parallelogram, the opposite sides are congruent. So that just gives us that 3y has to equal 18, and then y, of course, equals 6. So just kind of working with those basic properties of the parallelogram. Next, we're going to use those properties to prove that given a parallelogram with two diagonals, that the upper triangle here is congruent to the lower triangle. And in fact, that will prove that any triangle divided by the diagonals, the opposite triangles there are congruent. So, what do we know? Well, to start off with, we know, and again, we'll do this kind of informally, that segment AD is congruent to segment DC, because the opposite sides of a parallelogram are congruent. And so mark that on the diagram. We have that number, angle 1 is congruent to angle 2, and angle 3 congruent to angle 4, both by alternate interior angles. And therefore, the triangles are congruent. Triangle AED is congruent to triangle CEB by angle side angle. So it's pretty easy to prove, but that's going to allow us then to get some more properties. You may see some of them there already in regards to the diagonals. So theorem 8.7 says the diagonals of a parallelogram bisect each other. Okay, going back to our other diagram for just a moment here, we see that by corresponding parts of congruent triangles being congruent, we have segment AE congruent to segment EC, and segment BE congruent to segment DE. So very easy to prove that once we've proven that those opposite triangles are congruent. So a little coordinate geometry here. We want to find the coordinates of the intersection of the diagonals with given vertices. So of course we're going to start that off with a graph to show what we're working with. Here's the graph of that parallelogram. We can confirm that that's a parallelogram by looking at the slopes of the opposite sides and confirming that they are the same. So we want to find the intersection of the diagonals. Well, we just saw in the last theorem that the diagonals bisect each other. So if we draw in the two diagonals, we know that the point where they meet is the midpoint of both of those segments. So all we need to do is find the midpoint of one segment, and that will have to be the midpoint of both of them. So let's find the midpoint of segment NR. So the midpoint, if we look at the x's first, we have the average of the two x values. So n is -1 plus 5 and divided by 2. So the x midpoint is 4/2 or 2. And at this point, you should note that I did make a mistake there. Hopefully you caught that. That shouldn't be a 5. That should be a 3. I used the wrong point there. So -1 plus 3 divided by 2. So that's going to be 1. Now, I caught that mistake by looking at my graph and saying, you know, that really doesn't look like that x-coordinate is 2. And so I went back and looked at my work to determine what was wrong there. So the y-coordinate is, okay, for n we have 3, and for r it is 1. So 3 plus 1 divided by 2 gives us a y-coordinate of 2. And so the coordinates of the intersection of the diagonals then has to be the ordered pair 1, 2. And that agrees with what my diagram looks like. I could also go back and find the midpoint of MP and confirm that it is the correct point that way. Your homework for section 2 is page 415, 16 to 45 odd, and 46.